Hello and welcome back. Today in module number 7, I'm going to start talking about confidence interval estimation, but I also will talk about the introduction to how do we outline a hypothesis testing. In addition to that, I will cover the subject of basic structure of R programming, so it will be easier for you to see where the structure of R and implement that into your assignment. So overall, I hope everyone is doing well and everyone is ready for the class. And if you have any question, your job is to ask questions. My job is to answer your questions. So let's start. So the first part of the lecture, we will cover the construct and the interpretation of the confidence interval estimates for the mean. And I will also cover how do we determine the sample size necessary to develop confidence interval for the mean and the proportion. So a little summary of what we have covered last time. We said that confidence interval for the population mean when the population standard deviation is known and unknown. We had two conditions that needs to be met in order for us to calculate. So the confidence interval for the population determined the requirement size, sample size, which means that by determining the requirement sample size, we know exactly how to pursue when we are doing a sample from the entire population, taking a sample from the entire population. This is when point estimate and interval estimates come into play. A point estimate is a single number. A confidence interval provides additional information about the estimate. So the point estimate within confidence interval, lower and upper, and this is where we will play a little bit in order for us to adjust or to configure out where our sample can meet the population. So point estimate, when we estimate the population, we are talking about the mean and we are talking about proportion. With the sample, which is, we are talking about statistic and we are talking about point estimate, we have X hat and we have P. So as you can see, we have two terminologies or two singles that represent population versus the sample, where we need to learn how to calculate them in order for us to fit if we are taking a sample that represent the population. So how much uncertainty is associated with the point estimate of the population? The idea here is that the interval estimates provide more information about the population characteristics than does the point estimate. So such interval estimates are called confidence interval. So the confidence interval estimate is the interval gives a range of values, take into account the sample statistics and the sample to sample, and it's based on observation from one sample, and it gives information about closeness to an unknown population. And we are talking about, in these terms, we are talking about 95% and 99%. We can never be 100% confidence. So, an example. The population has a mu of 368 and the Q is equal 15. If we will take a sample with a number of 25, and so how do we calculate? So 368 plus minus 1.96 multiplied by 15 divided by 25 square root, which will give us a certain of 95% of the mean. So as you can see, when you do not know the mu, you use X hat to estimate the mu. So in this case, this is how we do that. And some of you ask me these questions online, and I try to explain that. I think this is a good example. How do we do that when we are talking about a population? So confidence interval example. The sample and the x hat, the lower limit, the upper limit, and contain a mu. Yes, in the case of yes, and when they contain of no. And this is how we will apply that in our cases. In practice, you can only take one sample of size n. In practice, you do not use the mu, so you do not know if the interval actually contains a mu. And however, you do not know that 95% of the intervals formed in this manner contain the mu. So based on it, based on one sample, you actually select that you can be 95% confidence that your interval contain mu. Then this is how we calculate. So the 95% confidence is based on the fact that z is equal to 1.96. So estimate process, random sample. We are talking about the population. We are talking about confidence that the mu is between 40 and 60. And this is how we will apply it when we will take a random sample. The general formula for that type of called estimate point, and we are doing that plus minus the critical value and the standard error. The point estimate is the sample statistics, estimate the population of interest. The critical value is the table based on the sample distribution of the point estimate and desired confidence level. And the standard error is the standard deviation of the estimate point. What is a confidence level? The confidence is the interval will contain the unknown population, and it is usually presented in percentage, and it is usually also less than 100%. Suppose confidence level is 95%, also written as 1 minus alpha, which is 0.95, or the alpha is 0.05. Relative frequency interpretation, and it is the contain of the unknown, is true the way for us to provide interpretation. A specific interval either will contain or will not contain the true parameter, or the idea of not probability involved in specific interval in that case. So the confidence interval, and some of you complain about my PowerPoint, so I try to clean it and try to make it as concise as possible. So the confidence intervals, it's contained the mean and the proportion, and with regard to the mean, we are talking about when Q is known or unknown, and that's where we are testing on it. The confidence interval for you, when it is the Q is known, is the following formula. The x hat is the estimate point. The z, by the power of alpha divided by 2, is the normal distribution, the critical value for the probability, and the square root, the Q of the square root, is the error. This is how we calculate that. Let's take an example. Confidence of 95% interval. It's 1 minus, and it will give us the equation. And this is where everything come into play with regard to where it stands and how we outline these critical values. So the point estimate is the 0, the lower confidence limit is and the left side is -1, and the right side is 1.96, and the x units is where we are trying to measure everything. So in this case, This is where we outline where we are confident with regard to levels. And so we have 90%, 95%, and 99.9%. So the idea here, the sample distribution of the mean, needs to be a match to it in that sense. So in this case, we are using different formulas in order for us to calculate that. An example. A sample of 11 circuits from a large normal distribution has a mean resistance of 2.2. Okay, so we know from the past testing that the population standard deviation is 0.35. So to determine a 95% confidence interval for a true mean resistance of the population, we will do the following. So the sample in this case is 2.2 plus minus 1.95 multiplied by 0.35 divided by square root of 11. And it will give us where the mu is standing with that regard. So where did I came up with the numbers? 2.2 is the mean, and plus minus 1.96 is the, we are want to have 95% confidence. So we are taking that as a starting point, and we multiply it by the standard deviation divided by the square root of 11, and that's where we come up with that idea. So we are 95% confident that the true mean resistance is between those numbers, 1.9 and 2.4, although the true mean may or may not be this interval. So the 95% of the intervals formed in this manner will contain a true mean. Okay, what do we do when we are talking about the unknown? So do you ever truly know that value? Probably not. So there is a situation where the Q is known, then the mu is also known. But if you are truly know the mu, there would be no need to get a sample to estimate that. And in that case, you need to be aware of that and make a footnote into your head, and I'll show you an example in few seconds. The other proportion, other aspect of the confidence interval is the population. And in this case, the interval estimate of the population can be calculated by adding the allowance for uncertainty of the sample proportion, the P. So in this case, the formula for that, we will recall the distribution of the sample proportion in normal if the sample size is large with the standard deviation, and we will estimate this with the sample data by doing the formula below. So together we will have a confidence interval endpoints. Under the lower and upper and lower confidence limits for the population proportion are calculated with the following formula. Plus minus z, and as we learn, there has to be the idea of the n is the sample size, the p is the proportion, the z multiplied by the q and divided by 2 is the standard normal value of the level of confidence interval. Let's do an example, and I hope that example will illustrate what we have done so far. So a random number of 100 people show that 25 are left-handed, like myself. So from 95% confidence interval for a true proportion of the left hands. So in this case, a random sample of 100 people showed that 25 are left-hand. From 95% confidence interval for a true proportion of the left, we will do the following: 25 divided by 100 plus minus. We want to have 95%, which is 0.195, and we will square root it in 0.25 multiplied by 0.75 divided by 100, which will give us smaller than 1.65 and smaller also from 0.34. So the interpretation, we are 95% confident the true percentage of the left hands in the population is between those proportion 16.51% and 33.49%. Although the interval from 0.165 to 0.3349 may, and I repeat, may and not may contain true proportion of the 95% interval from the sample size in that manner. So, how do we determine the sample size? We have for the mean and for the proportion. And so we are talking about the sample error. And the requirement sample error can be formed to reach the desired margin of error. In this case, it will be marked as E, with specific level of confidence 1 minus the alpha. So the margin of error is also called the sample error, and it is the amount added to and subtract to the point of estimate from the confidence interval. So how do we determine? I tried to illustrate that in this demonstration. So we have determined the size for the mean, and by calculating the calculation, we are able to say the sample error, the margin of error, and by doing that, we are determining this sample size. So in this case, not solved yet for n, to get the following formula. To determine the required sample size for the mean, you must know, first of all, the basic premises of that type of question. You must have the level of confidence, which determines the critical value of the z. We have to have the acceptable sample error, and we have to have the standard deviation. Let's take an example. The sample size example. We have the idea that it's 45. What sample size is needed to estimate the mean within plus minus 5 with 90% of confidence? So in this case is 1.654 square root multiplied by 45 square root divided by 5 square root. So in this case is 219.19, which is again required sample in this case is 220. Let me repeat again and go back to the formula. This is the formula that we are using to determine our sample size, and in this case we are giving some premises, we are giving some information in order for us to do that. And again, the 1.645 is the 90% confidence that we need to square root it. If it is unknown, can be estimated when we are using the requirement sample size. So the idea here is that we select a pilot sample and estimate with the sample standard of deviation. So when we do not have, again, it's not known, we have the idea, how do we do that? How do we apply that? The formula change a little bit, and by doing that, we are required to have the desired level of confidence, which determines the critical values. The accepting sample error still remains, but we are changing how we calculate that, and the true proportion of the events of interest. In this case, it can be Estimate with a pilot sample, if necessary, with a 0.5 estimate. So, how large a sample would be necessary to estimate a true proportion defective in a large population within plus minus 3% with 95% confidence, assuming that this pilot sample yields that P is equal to 0.12. So the idea here is, again, I want you to take a very close look how I use all the information that was given to me. I do not make up things. So 1.96 square root multiplied by 0.12 multiplied by 1 minus 0.12 divided by 0.03 will give us that the use n is 451, and in this case this is what it will need to do that. Let me give you one more example, and more correct example with regard to the accounts. We have a population of 1,000 accounts and wishes to estimate the total population value. A sample of 80 accounts is selected with an average balance of $87.6 and a standard deviation of 22.3. So find the 95% confidence interval, estimate the total balance. And again, lay out your foundation. What is n? What is small n? What is the x hat stands for? What is this, the s? And by doing that, you are able to estimate, and you, as I show you here, the entire procedure, you are be able to estimate that 95% confidence interval from the population total balance is between 82 to 92, and by doing that, you are be able to do that. In the R, the mean with a standard deviation in R is called Q norm. So the mean with a standard deviation using the summary is QT. And this is called function that every R studio and every R platform will recognize. So the mean with a standard deviation from unknown is called t-test. T.test. The proportion using the statistics in R is called Q norm. So let's take an example. This is the example. I have a container that contains different salaries, and we are asked to estimate the mean salary of all recently graduate students from the School of Information. So find 90% and 95% confidence interval for the mean. So the answer in this case, this is what we will do, and I lay out for you exactly what you do with regard to our calculation. And so we are 95 and 90% that there will be between the salary of 6,479 and 22,076 dollars in between. So this is the proportion. This is how I did it in R, and I hope that makes sense. I want you to occupy that, and I want you to be confident. Okay, moving along. We are now needs to start thinking about the hypothesis testing and how to formulate hypothesis testing on a simple test. So in this module, I will cover what is a null and what is alternative hypothesis statement. I will state what is a test statistics, what is a p-value, what is significant level, and what is one sample z-test, and what is the power in a sample size. So the terms: population, all possible values. Sample is the proportion of the population. You going to start moving into statistical interference, which is the next level after descriptive statistics. We're going to have two forms of the statistical inference. One is the hypothesis testing, and the other one will be the estimation. We are going to do that by calculation of the population versus the sample, and we are going to play with that and make sure that we are in same proportion in order for us to be sure that it is correct. So when we are talking about the population, we are talking about, in comparison, we are talking about a sample. The notion is the Greek of mu. In Roman or in sample, we are talking about x bar. And the calculate no, and in sample we do. So again, this is the big picture of the population. So let's start with what is a hypothesis. Hypothesis is a claim about the entire population. So the mean monthly cell phone bill in the city is around $42. So this is about the entire population. If we're going to talk about population proportion, we are going to talk about it will be equal to 0.68, and I want you to make sure that you understand the difference between them. The null hypothesis is the statement that claim or are said to be tested. So the average, this manner of the manufacturer bold is 30, and in this case we will say that the mu is equal 30. So it's always about the population and not about the sample. So, and I want to make sure that you understand that it's about the population and not the sample that you are taking. So the null hypothesis, or the H0, begin with the assumption that the null hypothesis is true. So similar notation of incorrect until proven guilty, and I hope you remember that, refer to the status quo or the historical value. Always contain equal or smaller or bigger signs, may or may not be rejected, and we will learn about that. The alternative is the opposite to the null hypothesis. So when we state something about the null hypothesis, the alternative will be the alternative hypothesis. So the claims, the status quo, it never contains equal or never contains small or bigger. It may and may not proven, and generally the hypothesis that the researcher is trying to prove. And I repeated it again. That's what we are trying to prove. So the hypothesis testing process, the claim, the average population in Tampa, Florida is 50 years old. The sample population, and define the sample mean. In this case, this is what we will do in order for us to claim, is this claim is null hypothesis or no, alternative hypothesis. So suppose the mean age is 20 and there is significantly lower than the claim mean population age of 50. If the null hypothesis were true, the probability of getting such different sample mean would be very small. So you need to reject the null hypothesis. In other words, getting a smaller mean of 20 is so unlikely. If the population mean was 50, you conclude that the population must not be 50. So the null hypothesis, again, if it is unlikely on the 20 side that the sample mean is this value, on the x hat size, then you reject the null hypothesis that the mu is equal 50. So this is the way for us to estimate, to portray, and to take a sample in order for us to claim about the population. If the sample mean is close to stated the population mean, the null hypothesis is not rejected. If the sample mean is far from stated population mean, the null hypothesis is rejected. So far is far enough to reject the null null hypothesis, and the critical value test is to create a line in the sand for decision making. If the answer to the question how far is far enough. So the test for statistic and critical values, we are taking a sample of the test statistics, rejection, and the critical value, too far away from the mean of the sample distribution, and we are having possible error in our hypothesis testing to make right decisions. The type 1 error is reject a true null hypothesis, which can happen. Consider various type of error. The probability of type 1 error is that it's called level of significance of the test or set by the researcher in advance. The type 2 error is the failure to reject a false null hypothesis. So the probability of a true type 2 error is, in this case, B. So this is the summary, again, the summary of possible hypothesis outcome that might be take into account. Do not reject the null hypothesis, no error probability when 1 minus the alpha, and type 2 error with a B, and reject the null hypothesis when you have the probability of mu or no error probability 1 minus the B. So the idea here is the confidence coefficient 1 minus alpha is the probability of not rejecting the null hypothesis when it's true. The confidence level of hypothesis test is 1 minus mu multiplied by 100%, and the power of statistic 1 minus b is the probability of rejecting the null hypothesis when it's false. So type 1 and type 2 relationship, it is when type 1 can occur only when a null hypothesis is true. Type 2 error can occur when a null hypothesis is false. This is how it goes, and the factors that affect that, and I try to illustrate that as much as I can with regard to that effect. So the level of significance and the rejections, and there's two tails test for that there is a rejection region in both tails. So we also need to talk about the hypothesis test for the mean. So when we know the mean, it is called the z-test, as we learned beforehand. And when we do not know where the mean is, which is the t-test. And in this case, I lay out for you what is the idea of the z-test and how to apply that into it. The critical value approach for the test is converting a sample statistic to a t-test, determine the critical z-value for a specific level from a table or computer, and decision row if the test statistics fell into the rejection region, the rejection of the null, otherwise we do not reject. And we have two trail tests, and again this is where we upper critical value, lower critical values, and how to do that. This is really important, and I want you to remember this is 6 steps in hypothesis testing. You are first state the null hypothesis, which is the H0, and you state the alternative H1. You choose the level of confidence. The level of confidence can be 90%, 95%, or 99%, and the sample size. And I showed you how to determine the sample size. You determine the appropriate test statistics and the sample distribution. You determine the critical value that divide the rejection or non-rejection region. You collect the data and compute the value of the test. You make sure, and this is the last step, make sure the statistical decision and the state of marginal conclusion. If the test statistics fell into the non-rejection region, you do not reject the null hypothesis, as I said before, and if the test statistics fell into the rejection, reject the null hypothesis. Express the marginal conclusion in the context of the problem. So let's take an example. Test the claim that the true mean of manufactured bullet is 30. And we are assuming that it is the Q is 0.8. So we have the null hypothesis is 30. The alternative is not equal to 30. So there is two trail tests. We are required to specify the desired level of significance. Suppose that it is 0.05 with 100 sample size of 100. We choose for the test. We start to identify the claims. We give a symbolic form that must be true when the original claims is false, and we are giving up the idea. So we are generating drivers who admit running red light is greater than 0.5. The mean height of professional players is at most 7 foot, and the standard deviation of IQ score of actor is equal 15. Those are examples to help you identify the null and the alternative hypothesis. The proportion of drivers who admit to running a red light is greater than 0.5. In this case, it will be a null hypothesis. Why? Because we have, it will be alternative. Why? Because it will be greater or smaller than 0.5. And the second one is the mean height of professional basketball players at most at 7 foot. And again, that can be the null hypothesis. And the third one is also equal to, is a null hypothesis. And so alternative in this case, the standard deviation of IQ score is equal or smaller than 15. And that will be the null alternative way to do that. The proportion, and again, I lay out for you how it lay out and how to identify that, so you have all the claims, all the steps in order for you to identify. So this is the end of module number 7, where I lay out the null hypothesis. What I will do is I will give you the assignment that I mistakenly gave you the last time, and you will apply that and try to do that with the R. And again, if you have questions, please do not hesitate to ask me. Until next time, enjoy and ask questions.